So in this video then I'd like to explain a little bit about how data is taken with the continuous wave NMR that we have in front of us here. So essentially what's going to happen is you see a couple things on the oscilloscope screen. Let me turn channel 1 off for a moment here. And the first thing you see is this sine wave on the screen. And what that is, that's that so-called wiggler magnetic field, which causes the main static magnetic field, which sort of sits where my finger is, and if you apply a wiggler to it, it sort of causes the net magnetic field to oscillate back and forth, something like this, around the central B naught that's set by the electromagnet. So this is the modulation field that you see in front of you. The next thing you see, if I just have it on channel 2 and I have the oscilloscope triggering on that. Now if I turn channel 1 back on, this is basically the NMR response that comes out of the coil. Sort of tells you if those RF photons were absorbed or not, as discussed in the lab manual. And so what we do to take data then is we set some current going to the electromagnet, in this case here 2.78 amps. And then what we do is we just get our hand on this frequency knob that you can see down here. This is the frequency knob, and we just start turning this until we see a response on the end, on the space. So like right there. So I think I was pretty close and I got lucky. So okay, so hopefully you see there's just a frequency knob and you can see the frequency. Let me zoom back in on the oscilloscope now. So this is sort of what you get on the oscilloscope display. And I'm going to turn the frequency knob a little bit now, and you can see as I go a little bit higher, the signal kind of goes away, and if I come back lower again, it sort of comes back. And so what you're after then is we're really close to that proton flip resonance. And again, the magnetic field sits here, and that wiggler field keeps bringing us too low and too high, and sometimes right on the resonance, but that's exactly what allows us to pull this experiment off. So these videos for taking data are incredibly hard to take because all of the settings on this NMR are very, very sensitive. I'm seeing the current drift, probably temperature effects as we go, that the frequency can drift a bit, and there's some sort of bizarre effect that if I turn the amplitude too far up or down, the frequency kind of disappears. I'm not sure exactly what all that's about, but in either case, we have definitely found the RF resonance, the NMR resonance. And what's important to do, and for the sake of getting a good result, is we always want to make sure that these resonances here are always equally spaced, because you figured if there is a resonance right here and you have a sine wave sweeping the magnetic field on either side of it, it should hit that resonance once and then twice every cycle, and it should be very symmetrical. So what I'm doing to ensure that is I have these cursors on the oscilloscope here, these measurement cursors here, and I'm just sort of lining them up with two resonances here until I sort of get a cursor width. I mean, I can definitely eyeball like something like that. You can tell they're definitely not evenly spaced. These two are bunched together, then there's a big space, and then these two come in again. And I'm just turning the frequency knob. Here's a bit lower in frequency, and I can see even if I just eyeball it, they are starting to get a little more equally spaced. And so the reason why I'm telling you this is because this is definitely going to dictate sort of what frequency I'm going to end up claiming my NMR resonance was at. So if I move these cursors back over, I'm sort of using them to line them up to both resonances, so they're sort of lined up to both resonances there that happened on one cycle of that sweep again. And so now I'm going to go over here, oops, wrong button. Now I'm going to go over here and see these two are about the same width too, same spacing apart. These two are about the same spacing apart, and these two look okay too. And the only reason I'm judging this is I just see that as I sweep to the resonances, both of them are sort of lining up with these dotted cursors here, these dotted vertical lines. These aren't so well aligned, but now if I go back to the original, see those have sort of drifted as well. See, they're not as aligned as they were, so I'm going to go back and tweak the frequency up again, going a little bit lower here to make them all kind of line up again. Good, that one's good. That one's good, that one's good. Yeah, this is looking pretty good. These are all look like they're really evenly spaced. So you'll see when I start taking data that I'll always sort of find a resonance, then I'll go and hit them with the cursors here to make sure that they're all equally spaced. And that allows me to sort of set a criterion for exactly what frequency am I going to choose to write down. So again, these videos are really hard to make because everything is really sensitive, but I think I can pull it off here. And also just keep in mind that there's also an amplitude knob down here at the bottom, this one right here, and there's of course the frequency knob that I'm turning most of the time. Let me just show you some effects of the amplitude knob here. So this is the amplitude of the RF applied. So if I sort of turn that, you see I'm turning the amplitude up, and for whatever reason the signal is getting smaller, probably because I'm not quite on resonance anymore. As I turn the signal down, then it gets quite large there, almost have to click the oscilloscope to the next level, next volts per division. That's fine, but I still say the core cutoff here is if these resonances are equally spaced. I see it has drifted quite a bit. Just when I'm talking to you, that's what makes this kind of difficult. Let me bring them back. I'm having my hand on the amplitude knob at the moment, and so I'll just sort of realign it. But that's sort of a tour of how data is taken. And my only point is that when you come up here and start doing the NMR, You're looking for the resonance up here. In this case, I'm just deciding to use the oscilloscope cursors to make sure they're equally spaced. But you have a frequency knob you can turn, you have an amplitude knob you can turn, and they all seem to be very, very sensitive. So we hope the data comes out okay as we go. The other knobs, which we don't fiddle too much with here, of course, the B modulation, that's the one that caused the magnetic field to sweep back and forth the way I've been doing here. There's a fast and slow sweep and an amplitude. Neither one of which has very much effect on the signal. So if I go to slow sweep, maybe that's just a little too slow for us. I'll keep it on fast sweep there. But of course, the amplitude of the modulation, you can see that changing there. It doesn't have a lot of effect on the resonance. It doesn't really matter too much as long as you're sweeping past the resonance so it can show up. That's really what's important. And the last knob that's on sort of this magnetic field sweep is this phase knob here, which allows me to say to move the resonances entirely left or right on the oscilloscope. It's sort of like just a phase that would go into a trigonometric function to sort of apply how quickly the modulation sort of went up, or not how quickly, but at what time it actually started to go up. That's what the phase does, right? Just sort of shifts the sine wave left or right. So you sort of have that in there as well. So it's very sensitive. As you can see, I just back on the frequency knob here as I change the frequency, it's just jumping all over the place until it kind of stabilizes. And that's even with the oscilloscope doing a bunch of averaging at the moment. Let me see what I have that on. I have on the averaging, go back to acquire over here, pardon me, acquire right there. I'm averaging two signals, two traces, but if I go to normal, well, it actually doesn't look too bad on normal either, so maybe the averaging wasn't quite that important. So anyway, that's the way the data is going to be taken, so just look forward to some data, and you'll see some effort to make sure the peaks are equally spaced with the oscilloscope cursors, and some back and forth on my hand here between the oscilloscope cursors and the frequency down here, and you'll always know when I'm going to sort of declare victory, when I sort of stop moving things and just pause a bit. That's probably the frequency you should write down, but watch very carefully, because also the equally spaced bit with the resonances on the oscilloscope and the frequency are definitely going to go to your uncertainty in the frequency that you should report as you write down the frequencies that we're sort of declaring victory at as we find some equally spaced resonances. So it's quite difficult to do. And as you take the video, you'll see that I'm visiting all kinds of currents here and all kinds of frequencies. I'm just trying to find as many resonances as I can. And they're very close together. So it turns out like if I have a current of something like 3.25 amps and something like 3.3 amps, the frequency is going to be very different. So it isn't like I'm going to take very large steps in current, but you'll see that as well. So even if I turn this current knob now just a tad bit, see the resonance is entirely gone. I'd have to go finding it again to 2.56 amps versus what it was before. Okay, so that's sort of how the data is taken.